Hi, I am audible, right?
Yes, sir.
Okay. So first of all, actually, I got a request from many students. They are saying that this topic, mainly that relation and sets, uh, that cardinality, these are not available. That's mean I did not give any reference. So they wants to do more practice, but they do not get the problems. But I think, see, this is an easy solution. So if you just search in the internet, maybe in the Google, then you will find many say PDF, and where you will have many problems. You can try those problems. For an example, see, so I cannot give any references because I did not follow any book, as I told you. For an example, you have this Google page, right? You can see that. Oh, sorry, I did not share. No, I presented my screen. Fine, right. Now, if you just search that, say, cardinality, say PDF, search that, then you will find many notes on cardinality. For an example, you can go to this. See, you will have some notes. You can follow that problem from here. For the theory, you should stick with my notes and which I give. Otherwise, which I use as a result, someone can use as a theorem. So better to follow that one, and then you can find. See, you can get everything here. See that cardinality of this equal cardinality of this, how they prove this one, and there are, see, some exercise, extra exercise. You can solve these problems by using the theory which we developed. This, see, countable and uncountable sets. And again, you have some exercise here. You can find lots of exercise here. And similarly on cardinality, you can see whatever. And today we will prove this one. So everything you can prove this one. So everything you will find here as well. And you can try to solve this one. See, this is this one, that Bernstein showed a theorem which we proved. So you can find everything in the Google, because how did I prepare the solution set, that lecture one, lecture notes. So I just so which topic I wanted, I searched Google and I got some problems and I solved by myself. And you can also find that exercise from this one. And similarly, if you want to search, say, order relation, or say order set, PDF, every anything, you can find something. You can find a one, this one. Then again, you will have a notes. See, you can find some which I did, that upper bound, lower bound, least upper bound. So you can find this one. What is the least upper bound? What is that? Right? See, there is no least upper bound. So you have a least upper bound problem here as well. So if you search Google, you can get everything. So you have to just, if you want more, see, I told you that the lecture notes we are giving. So I have given lecture notes, and those lecture video of the lecture notes I am giving also live. So you can find the recorded lectures. I also gave you some YouTube link of my lectures, right? In that YouTube link, if you go there, you can find some extra problems as well. I do not remember if there is any, but you can find any extra problems there as well. So you can go for that one, and you can stick with the lecture note. And also in the during the offline lecture, we generally did not give any lecture notes, right? We just gave the lecture talk. So that's the reason we generally need the what are the references book. Otherwise, if you don't write during the live lecture, then it is difficult. But nowadays we are giving you lecture notes and we are giving you the recorded video. I think that is sufficient. And also we have some tutorial sheet as well. And if you want to solve more problems, you just search in Google, you will get everything. And for those reference I can give, I will give. Definitely I will give. For an example, for the logic part, I told you that I generally follow that Roshan book. And you see that everything I followed from the Roshan book. But from this part, mainly that set and cardinality and this relation, so in not any single book I have followed. So every content are the same. So for an example, if you find that search in Google, you can see that that content is almost same, which I taught during the lecture, right? So just if you want to solve more problems, then search Google and you will get the solutions. Because if you say this is a diverse subject, or you can say diverse course, you have graph theory, you have combinatorics, you have a set, you have relation, you have logic. So everything, every good thing you cannot find in a single book. That is the problem. So for different portion, we are referring different book and different may say notes and places. Okay. So I believe that whatever the content I taught during the lecture, that is sufficient. If you watch the lecture and watch the video and read the lecture notes very carefully, definitely you will solve all the problems during exam, because that will be related to that one only. And if you want to solve more problems, you just search in Google, you will get everything. Okay. So I hope there will be no more confusion on that. Okay, fine. So any question on that or any doubt, or do you want to say something? Yes, Shubh, do you want to say something?
No, no, sir.
Okay. Okay, just search Google.
Sir, you are muted.
Oh, sorry. Yeah. So today, right. So we will see this is the last lecture on cardinality, and your minor syllabus will be up to today's lecture. And today I will send you all the details regarding the exam. Okay. And in the next day, that is before minor, you will have another lecture, and I will start combinatorics on the next Thursday. So this is the last lecture for your minors. So obviously focus on it so that you don't need any reference further. So today I start with Cantor's theorem. So what he says actually, that Cantor, he proved that for any set A, cardinality of A is strictly less than cardinality of power set of A. So that's mean he proved that there is an injective map from the set A to the set power set of A, but there is no bijection from A to PA or between A and PA. Okay. And obviously this is clear. This is clear if A is a finite set. So proof. So this is clear if A is finite. Right, we know that if A has n element, then power set of A has 2 to the power n element. So we know that we have that counting. Is there any question? Okay. Can you schedule Thursday lecture as revision or leave that as a revision day? No, I cannot give that one because we have a limited number of lectures. So what is my plan? My plan to finish early. See, minor is not an important exam, but major is the one. So my job is finish the syllabus as early as possible Probably the last two lectures I want to I gave as a revision one, but not this one. You can what you can do. So after minor, you will have a lot of gap, and then if you don't want, say, you just attend the lectures on the Thursday lecture, and you don't have to read that. You can read that after minor. Okay, since we have packed schedule, so we cannot leave Thursday as only the revision day. Otherwise everything planned will be, we have to change. For an example, we have a quiz on 11th, I think 11th October, so that has to be changed, and everything will be changed. Since I have a perfect plan actually for this course, so I have planned everything. So in which day I will teach what, so I have planned everything. And probably the 11th, not 11th or 8th, yeah, probably the 8th of November will be your last lecture, and then 11 and 15, no, 11 and maybe there is another day, I think 14, 11 and 14, that will be the revision day. Okay, and for this minor, that exam will not be that difficult, because that portion is not a difficult one, right? That logic part is very simple. Okay, so we know that this is, yeah, if A is finite, then it is clear, because if A has n element, then power set of A has 2 to the power n element. So anyway, you can, so main focus is the infinite, if A is infinite. Anyway, the proof will work for the finite and infinite for on both, okay? So we define, so let us define a function if A to power set of A, okay, we by just define by f of A goes to just singleton A. Now if A belongs to A, then singleton A is a subset of A, right? So that implies, so you can say that this is belongs to power set of A. Okay, and clearly this is injective, and clearly this is injective. F is injective. Okay, now since A is injective, F is injective, so therefore cardinality of A is less than equal to cardinality of power set of A. Okay, now we prove the second part, that is there is no bijection between them. Now if possible, let's say H from A to PA be a bijection or bijective function. Okay, so if possible, there is a bijective function from A to FA, then we will get a contradiction. Okay, so first note that for each A belongs to A, what is a HA? HA belongs to PA, right? So that's mean HA is a subset of A. So that implies HA is a subset of A. Okay, so A belongs to A and HA is a subset of A. So that's mean actually you have some cases, right? A maybe belongs to HA or may not be in HA. So we define a set S such that all the A such that A not belongs to HA. Okay, so we are taking all the elements from A such that A is not in HA. So obviously this is a subset of A. So that implies S belongs to power set of A. Okay, now see we have a bijective function this, and S belongs to power set of A. So what does it mean? That's mean it should be surjective, right? So that's mean there exists X in A such that H of X equal to S. Why? Since H is bijective, or you can say surjective, or you can say bijective. Whatever you want to say, you can say. But since it is bijective, so you can get an element X in A such that Hx equal to S. So up to this, is it fine? Up to this portion. Now we have a beautiful contradiction. Now what are the possibility? So what are the situation? So first of all, X belongs to A, right? And Hx, which is S, right? It is a subset of A. Okay. So that's mean we have two possibilities. Case one, so X is in S, and case two, X not in S, that is X belongs to A minus S. So right, so we have two possibilities. Now in each possibilities, we will get a contradiction. So now look at the first possibility, case one. So X belongs to S. Okay, now what is S? S means all the element A such that A not belongs to H. Now since X in N S, that's mean by this property X not belongs to Hx. And what is Hx? That is S. So this is a contradiction. So we assumed X in S and we get X not in S. So this is a contradiction. Now go to the case 2. Now X not in S, right? So what is X? S? S means equal to H of X. So that is X belongs to A and X not belongs to H of X. Now see the definition of S. What was the definition of S? See, this is the definition of S. So the S is the collection of all the element of A such that A is not in HA. So since X is follows that property, that's when X belongs to A and X not in HX. So therefore X is in S. Now that will imply X belongs to S. So again we have a contradiction. So we assumed X not in S and we get this. So again this is a contradiction. So that imply H cannot be bijective, or you can say it cannot be surjective. So we are done. So
Sir, so, we define the function x is equal to s, right? This R4.
Tell me.
So do we define this function R on it is a like x belongs to a such that h of x is equal to a? Means why do we define this? On what
This
observation?
one. This one.
Use yes sir, these two. H of x is s and s.
This one.
So I think this is a conclusion of the above. So means how we define this above one? S
So
is
this
equal
one.
to
No, we just assume we just see that is it. That is the reason it is a famous theorem. So no, normal people could not do it, right? So Cantor's prove it. So that was the trick. So he constructed one set S, right? He constructed one set which which is in the power set of A and which does not have any preimage. So he actually proved that the map H is not surjective. So if you define any map A from A to PA, that cannot be surjective. He proved that. And that is the clever way he has defined the set S. So this is the way he has defined S. Okay, and obviously S is a power set of S is an element of this PA, but S does not have any preimage. Okay, and we assume that here if S has a preimage under the function H, and if that is X, then we will get this type of contradiction. So therefore H cannot be surjective. So that's mean, in other words, you can say that the set H cannot have any preimage. Okay, and the way you have defined this set S, this is a trick. You cannot say that why you have defined this. So this is the trick of this whole theorem. And that is a famous trick. It is not just a usual one. So that is the reason it is given that it is a Cantor's theorem. Okay, he won that theorem by giving that trick.
Sir,
Yeah.
sir, I'm not understanding this. X belongs to A. This means that X does not belong to H of X. Then how H of X is equal to S?
Case 1 or case 2?
No, sir, here this in the same one, these three lines. Yes, sir, the
This one. This one.
X belongs to A. There exists X belongs to A, such that H of X is S. Now, if X belongs to A, it implies that X does not belong to H of X.
No. See, if S is so from this construction, it is clear that S is a element of power set of A, right? S can be empty as well. Even an empty set belongs to the power set of A. Okay, so we cannot saying that S is not empty or something like that. S can be any set including empty, and that is belongs to the power set of A. Now we are claiming that if since given that H is a bijective map, so that means it is surjective, so that S must have a preimage, and let us consider this X is the preimage of S. Okay, so that's mean Hx equal to S. Okay, but what is, so I am writing this line only. So we take X belongs to A, this, and Hx equal to S. We are writing this. Now X belongs to A and Hx equal to S, and this is a subset of A. So we have two cases, right? So we have a point X and we have a set S, which is subset of A, and we know that X is in A. So therefore we have two possibilities: either X will be in S or X not in S. And we are claiming that in both we are getting contradiction. That's when X is neither in neither in S, and X is in S as well. So that's mean it cannot be in both. So what we are proving actually, so this and this, and in both we are getting contradiction. So that's mean X is not in S and X is not in A minus S as well. So that's mean that X does not exist. Okay. Did you get? This is a proof by contradiction. This is a proof by contradiction. We assume that if H is surjective, then there exists X, or you can right. So we are assuming that H is surjective, or you can here saying that from this. So if H is bijective, then we are getting this, and we are getting a contradiction. So therefore H cannot be bijective. Okay. See, we have already assumed that this one. So we have already assumed that, see. So if possible, let H be a bijective function. So we have already assumed that H is a bijective function, and we are getting a contradiction. So therefore H cannot be bijective. And why we are writing that? Because H is a bijective map. Yeah, still, yeah, I don't know. So are you asking this one, or do you have the another doubt and I am going the wrong direction?
Yes, I got my point.
Okay, okay, thank you. It is good that I could able to explain.
Sir, can you explain the case 2 once again?
Okay, good. So I always happy if you ask the questions, that's when it feels that I'm teaching. If you don't ask anything, it feels like I am just reading. Okay, so the case one was X belongs to S, and the case two was X not in S. And these two are the uh, two parts, right? And their union will be the all the possibilities. Now suppose X not in S. Okay, X not in S. So what is S? S is X HX. So that's mean X belongs to A, right? Why X belongs to A? Because that was the condition. So there exists X in A, right? So therefore X belongs to A. Now X belongs to A and X not belongs to HX. From this, that was the case 2 actually. So this is the case 2. X not belongs to HX, and that is the given. That is X in S. But both imply X belongs to S, because that was the definition of S. So definition of S was all the collection of the elements of A such that A not in H of A. All the collection. Now since X satisfies this property, so therefore X in S. So this is the contradiction.
Okay, sir, got it.
Okay, thank you.
Sir, wait, can you go to like the starting of the proof? 1 minute.
Huh. So if
Okay, so
possible,
sir, like here, are we ever using the fact that this thing h of a is injective?
no, we are not using that. We are just here we are
Okay,
proving
so
that
we're just
it is
okay,
not
so this proof
surjective.
is basically that there cannot exist a surjective function.
Right.
Okay.
So we need that one. We need to prove, because there is an injective function, and if there is a surjective function, then there must be a bijective function as well. Do you remember the last time we have proved that? Okay, I can recall that proof. So
Yeah,
that's when
yes, sir.
actually
That
you have to
Schroeder
prove it
theorem, I
is
think.
right, right. No, not Schroeder theorem. Schroeder theorem says that both are injective this way and that way. The reverse way, both are injective. Then you will have surjective. But since we have another theorem, okay, I can rewrite the theorem. Then all the confusion will be over. So the following are equivalent. So first one is A and B say non-empty set. So there is a bijection F A to B. So there is a bijection. Okay, there exists. Now that is equivalent to that. There is an injective function F from A to B, and okay, there is a different name. There is an injective function B H from. Now this equivalence is the at Schroeder-Bastien theorem, and you can also prove that this one. So there is an injective function G A to B, and there is n, there is a, surjective function J G H say P A to B. So these three are equivalent. So that's mean if you want to show that there is a bijective function from A to B, it is sufficient to find there is an injective function from A to B and there is a surjective function from A to B. You prove there is an injective function from A to B and there is an injective function from B to A. Okay, so that's mean all of these three statements actually says that cardinality of A and cardinality of B are same. Okay, so that's mean we prove that this n, that cardinality of n is strictly less than cardinality of power set of n, and again it is strictly less than, say, actually we'll prove that is R. We'll prove that. Okay, then power set of R okay, I got disconnected. Now I
Is there any
think it is
problem on my side or on your side? Because your screen is freezing sometime in between.
sorry.
Actually,
Yeah.
there is a problem. I think I don't know whether it is my side or on your side. That the screen sometimes got freeze in between.
Okay, there was a problem. Now it was a problem from my side now only. So I got disconnected for a while, maybe for few seconds. Okay, so what I'm saying that, so since we have proved that cardinality of A is strictly less than the cardinality of the power set of A, so therefore we have this, that cardinality of n is strictly less than cardinality of power set of n, and we will prove that that is equal to cardinality of R. We will prove that, and then again by the Cantor's theorem we have this. Okay, and generally that is denoted by LF naught. It is not n actually, it's something kind of n, and this is LF1, this is LF2 in this way. So these are the symbol, they generally use that. Okay, and the last,
Sir, between like N1 and N2, like there is no set that comes in whose cardinality is between those two, huh?
no, so that we cannot prove it, that is a continuum hypothesis. So we explain, we
Okay,
first
so
write that one.
it's what? So it's not yet to be proved.
No, but we assume that, we assume
Okay.
that. So actually it is not proved. No, you cannot, it is not proved. It is given, so one, someone proved that it cannot be proved.
Okay.
Okay, so you cannot
Okay,
try to
fine.
prove it.
Wait, isn't that technically a proof?
Which one?
Like if this proof cannot be proved, that means you
No, someone
cannot
proved
find a
that.
set who is
No.
between those two.
Someone proved that the hypothesis cannot be proved, and someone proved that the hypothesis cannot be disproved. So therefore, so people assume that it is a hypothesis, and we are assuming that this is true.
No, sir, like isn't that all isn't like if it cannot be disproved, like one way to disprove it is by counter example.
Right.
So if you find a set whose cardinality is between those two. So if you cannot disprove it, meaning you cannot find a set between those two. Meaning that no set exists. So isn't that technically a proof?
No, that you cannot say directly that one.
Why not?
Sure, the problem is that whenever we have this kind of thing, so you cannot use most of the mathematical tool. So that's mean you do not have sufficient mathematical tool to prove this one. For an example, R is complete. For an example, R has a least upper bound. You cannot prove that. For an example, the mathematical induction, you cannot prove that. but you have to assume that one for an axiom, because you do not have some sufficient tool to prove that. Maybe this is equivalent to something else and which also has been taken as an axiom. So I do not know, I have not seen that continuum hypothesis cannot be proved and cannot be disproved, this kind of result I have not seen. So generally when you have this kind of result, so that is equivalent to something which is an axiom. For an example, mathematical induction, you cannot prove it because that is equivalent to the Eulerian principle of n. And similarly, R has the least upper bound property, you cannot prove that. So we generally assume this as an axiom. Okay, so actually you do not have sufficient tool to prove this. So in this way, one can say actually, so this hypothesis cannot be proved and cannot be disproved. So it cannot be disproved means, so to disprove you need some tools which may not exist. Okay, I just write what is a continuum hypothesis, what is the. So there is no set whose cardinality is strictly between the cardinality of n and the cardinality of R. And we assume this as an axiom, as it cannot be proved or disproved. Okay, so it cannot be proved in the sense that you do not have sufficient mathematical tools to prove it. Okay, so the main thing are left is that this one. So this, that power set of n, the cardinality of power set of n is same as the cardinality of R. So this one. So these are the, you can treat this as a problem. Okay. So first of all, we prove that because that kind of problem may come during exam, because that is not a theorem. So that is a problem. So power set of n equal to 2 power cardinality of n. So that is, there is a bijection h from power set of n to this one. Now what is this one? That 0, 1 power n. So it has actually two, actually this denote the set of all functions f from natural number to 0, 1. Okay, and also we can think the set this as a collection of all sequences with entries 0 and 1. Okay, so both are equivalent. Why? Because if you have a function For an example, this. So that's mean you have F0, sorry, F1, F2, F3. So you have this, right? And so that's mean you have some X1, X2, X3, this, where Xi belongs to 0 or 1. So this is the same as the set of all functions from natural number to 0, 1 can be treated as set of all the sequences with entries 0 and 1. Okay, fine. Right. So can you guess? So what will be the function from this to this? So how to define this one?
Like uh, does the natural, if the natural let x be an element in P of n.
Huh? Say A is it?
Okay, let A belong to P of n,
Huh.
and then we'll define the sequence xi as xi is 1 if I belongs to A and 0 if I does not belong to A.
Right. So that is your obvious. That is your guess, or right? But that is a obvious one. Okay. So that is a obvious guess to give this one, this bijection, and it will work. So what is that? So actually it has a name. It is called generally, sometimes it is called a characteristic function. So let A subset of n. Okay. Now define a characteristic function chi A, which is a function from natural number to 0, 1, in that way that chi of A, that n, that will be 1 if n belongs to A and is 0 otherwise. Okay. Now just define H power set of n to this by A goes to chi of A. Okay. Now you can see that this is bijective. Now also this is also trivial to prove that this is a bijective map. Why? So let AB belongs to power set of n. Okay. So that's mean, so say such that chi of A equal to chi of B. Now what does it mean? So that's mean chi of A n equal to chi of B n for all n belongs to natural number. So that's mean chi of A n equal to 1 if and only if chi of B n equal to 1. In other words, you can say that n belongs to A if and only if n belongs to B. So this is just an observation. Okay, this is just an observation. Okay. Now now we'll prove the injectiveness. Now if A is not equal to B, what does it mean that A is not equal to B? So that's mean, so there exists M belongs to A such that M belongs to B, or you can say either this, or there exists M belongs to B such that M not in A. Okay, so that is the meaning of A not equal to B. So that's mean, right? So either A will have an extra element or B will have an extra element. Okay, so that's mean in either case we have chi of A M is not equal to chi of B M. Right? Because in the first case, chi of A will be 1 and chi of B will be 0, and in the second case, chi of B will be right. Chi of B will be 1 and chi of A will be 0. So they are not equal. Now since they are not equal, so therefore by this observation you can say that this one chi A is not equal to chi B. Since at least one point they are not equal, so that's mean chi A is not equal to chi B. Okay, so therefore it is injective. So thus S is injective. Okay. Now how to prove the surjective? Now surjective. So now let G belongs to this n. Say 0, 1.
So what was chi of A function defined earlier?
Chi of A means it gives 1 when the value is in A, and otherwise it will give value 0.
So it was defined from A to what?
No, no, not A to what? Chi A is defined from n to 0, 1. Okay, such that chi of A n equal to 1 if n belongs to A, and it is 0 if n is not in A. Fine.
Okay, sir, here we proved chi of A to be injective, na? Not P of n.
Sorry.
Here we have proved the chi of A to be injective.
No, no, no. What does it mean? So that's mean H of A is not equal to H of B. Okay. So that is the proof, right? So if your A not equal to B, then HA and HB should be different. Is it not clear?
But why actually not equal to each other? From where we are getting it?
Sorry?
From where we are getting it? H of A not equal to H of B.
Because what is the definition of chi of A? We have defined na, H of A equal to chi of A. So this we are defining. What is your doubt? I did not understand. What is your doubt?
Why we define H of A equal to chi of B?
We need to find a bijective function, right? We need to function a, what is the problem? Problem is you have to show that this and this has the same cardinality. So that's when we prove that there is a bijection from this to this. And this is my bijection. And we will prove that if we define in this way, then we will prove that H is the bijective function. Not clear? Hello?
Sir, actually we need to prove like power set of n prove 0, 1 to the with a cross product with n time is an injective function. We are proving that A is an injective function.
What you are saying then? I did not get your question. We have to prove that power set of n, okay, and 0, 1 power n both have the same cardinality. And this is actually this right side is the set of all function from natural number to 0, 1. Okay, and this the left side is power set of A. And how we define a function from this to this? We are defining if you take any element from power set of A, that's mean A, which is a subset of N, and we are defining H of A equal to chi of A. And we will prove that H is bijective. That's all. And that if we can prove that H is bijective, that's mean power set of A and this set both have the same cardinality. Yes, tell me. So what are you saying actually? I did not get. So is that clear or?
Yes.
Okay. See what we are trying to prove. We are trying to prove that power set of A has this cardinality. Or in other words, we will prove that there is a bijection from power set of A to this. And this is the set of all functions, okay, from natural number to 0, 1. So that's mean we have to give a function from power set of A to this. And we define a function H such that H of A equal to chi of A. So what is A? A is a subset of N. That's mean A is an element of power set of N. And what is my HA? HA is chi A. That's mean chi A is a function from natural number to 0, 1, which is in this set. And we are defining chi A in this way. So if N is in A, then we define it as 1. If N is not in A, then we define 0. Now we define in this way, and then we define that H is injective. Because if A is not equal to B, then we prove that chi A is not equal to chi B. So that's mean H is not equal to HB. So therefore H is not injective. Sorry, H is injective. Okay, so we prove that H is injective. Now we prove that H is surjective. So that's mean we take an element from this one, and then we will find a set A such that H of A equal to G. Okay. Now can you tell me how to find the set A? What will be the set A? Can you guess it?
Empty.
If you take empty set, that will not go to the G, right? What is empty set? So chi of empty set is a natural number to 0, 1, right? Now what is that set? So that all the element it is 0 for all n. So this is a 0 function basically. Now guess it. Guess another one, another set. So that H of that set will be G. That is not a difficult one.
A collection of all the elements such that g of let's say x, then g of x is equal to 1.
Right. Just in short, just take G inverse 1. That's all. Right? What is G? G is a function from natural number to 0, 1. Now just take S equal to G inverse 1. That's all. That inverse image of 1. Then see, then G of n will be 1 if n belongs to S and 0 if n not in S. So that implies G equal to actually chi of S. So that is H of S, and this is subset of n. So that implies S belongs to power set of n. So H of S equal to G. So we are done. So H is surjective. fine it is? Is that fine?
Yes, sir.
Okay. So that's mean we proved that cardinality of power set of n equal to cardinality of that one. No, which is expressed actually as 2 power n. So that is just a expression. Okay.
So why
So
you take one element like G inverse of one? Why we take a specific element? We should have for general G, no? For any x belongs to 0, 1, it should have inverse image. But we are taking a like a specific element. Only
no, we
set
are not
of
taking specific element, right? We first take any arbitrary element from this. Okay, so what was your domain? I think you are confused with what is your domain and codomain. So H is a function. Your domain is power set of n. And what is your codomain? Codomain is this one. Right? Now we are taking an arbitrary element G from this. Now what does it mean? G from this set. So that's mean G is a function from this. N to 0, 1.
but G will be of the form like 0, 0, 0, 1, 0, 1, or means the string of 0 and 1, na?
No, you cannot show. You can think in that way, but you generally do not think in that way. So G is a function from G into 0, 1.
So I
So it,
cannot get it.
huh?
What is G? I'm not able to understand it.
So G is a function from natural number to 0, 1.
So you said G is an element here, na?
G is an element of this set.
So what will the G look like? I mean, how the G will be?
So because G, you cannot see G, right? Because G is a function. But you can express G as a, you can express G as a in this way. G1, G2, G3. You can express this. It is an equivalent, but it is not the equal, right? So that's when if you know all the values of this one, that sequence one, then you can know the value of G. So G just a function. Into what is your this notation? So this is the set of all function from 0, 1 to n. Sorry, n to 0, 1. Okay, forget about everything. First tell me what are the element of 0, 1 power n? What are the element of this? This is the set of all functions f from natural number to 0, 1.
It's okay, okay.
Okay, I told you. So this set of all functions is equivalent to set of all sequence of entry 0, 1, 1. I am not saying that G is a sequence. You can express this because you can. This is equivalent, right? So if you know all the values of G at the in the natural number, then you know what is the function because your domain is n. If you know the values at every point of n, that's when you know the function.
Sir, also one doubt that we have to prove the coordinate. Means we should have defined the function from this power set of n to 2 to a power cardinality of n. Na? Why we are defining to this 0, 1 to the power n?
No, no, you are saying that no, no, no.
So because this is my definition that the set 2a and b have same cardinality if there is a function bijective function from a to b. So here b is like 2 to the power cardinality of n, right?
Right. So see, what is that? So you know that one, right? So I am not okay. You forget this one. I got it. What is your point? You are saying that power set of n, that is 2 to the power n. So this is trivial. You are saying that because you know that. So power set of any set S, cardinality of power set of S equal to 2 to the power n if cardinality of S equal to n. So it is known if n is a finite number. That's mean if S is finite.
But we
Okay?
know the cardinality of n, like, because it is countably infinite.
No, this is true for the if S is finite, then this is true. We know that. That is a trivial proof for that one, right? You just can count by using combinatorics. That power set of S is 2 to the power n, where S equal to cardinality of S equal to n. Now we want to generalize this for the infinite case as well. And this is a notation. This is just a notation. So there is no meaning of this because that is infinity. What is 2 to the power infinity? That is again infinity. So we are not saying that this is just a notation. So there is no mathematical meaning of this one. So this is just a symbol. This is just a symbol. Okay, we are actually trying to prove this one. So if you want, we can change our theorem. That problem, we can forget about this. Cardinality of this equal to cardinality of 0, 1 power n. This. Okay, so this is our problem. We are proving that cardinality of power set of n is same as cardinality of this. That is sets of all function from n to 0, 1. So that is our problem.
Okay, but that was actually the main thing is was confusing in me.
Right. And this is just a notation because what is this is valid for the finite case, right? If n is finite, since your cardinality of n is infinite, so there is no meaning of 2 to the power infinity because that is again infinity. So this is just a symbol. Okay, better that you ask so that I clear that out. Okay, so we proved that this one power set of n, this is same as 0, 1, this, both cardinality. Okay. Now we will prove that by this way. So this is same as cardinality of R. Okay, first prove that cardinality of 0, 1. This interval. Okay, it is proved. It is now will prove. Okay. Now how to prove this one? Now we will use one theorem. So we find one injective and one surjective function from 0, 1 power n to this. Now, can you give me one, say first of all, one surjective function from this to this? Can you give me one surjective function?
After the point, the string will repeat 0, 1. String will map to that number in real part.
No.
Like sir, like 0 point the sequence, like it'll be like a binary in like in
Yeah,
binary the
exactly.
number
It
from
will
0.
be a binary representation. So how do we define this one? Now define, say capital F 0, 1, this a function to this one by f of, say, f, this is a function, okay, equal to summation n equal to 1 to infinity f of n by 2 to the power n, where f is a function from natural number to 0, 1. Ups. 0.01. So that's when, so that is fn, that is either 0 or 1. So this. Now can you tell me why this is a bijective function? Sorry, why this is a surjective function?
Sir, because like any decimal, if you write in terms of binary, you'll get like an
Exactly,
infinite sequence.
exactly. Yeah, that is the answer. That is the answer. So that's mean any number x belongs to 0, 1 has a binary representation. So x equal to 0 point b1, b2, b3, b4. This it is in binary, where bi belongs to that 0, 1. Okay. Now just define. So which is same as, what is the meaning of binary? Which is same as summation n equal to 1 to infinity bn 2 to the power n in decimal. Okay. Now just define. Now let f 0, 1 defined by f of n equal to bn for all n. In this way you can define f, so that imply, or you can say g if you want a different function g, that imply capital F of g equal to summation n equal to 1 to infinity g of n by 2 to the power n equal to summation n equal to 1 to infinity bn by 2 to the power n, and that is x. So this is surjective. So that imply f is surjective. Okay. Now can you tell me, is it bijective as well? That means is it injective?
No, sir.
No. Why?
Like 0.1 and 0.01111111 are the same value.
Exactly. So in other words, so this is not here. F is not injective, as 0.1 and 0.0111 are same. In other words, so let A equal to only singleton 1 and B equal to 2, 3, 4 in this way, going that, then capital F of chi A is same as capital F of chi B. But chi A is not equal to chi B. So you have two functions, chi A and chi B, where chi A and chi B are not same, but their value are same. The value are same in the sense that that will be your only one this is, so it is 1 by 2, and this is 1 by 2 plus 1 by 4 plus, sorry, 1 by 4 plus 1 by 8 plus 1 by 16 plus dot this, and this is again 1 by 2. And give 1 by 2. Are same, we better to say that in binary. In binary. So therefore we get a surjective function but not injective function. Okay. Now similarly, can you define a say injective function from this to this? So we define a surjective function. Now can you define an injective function from this to this? Yes. Just replace 2 to the power n by 10 to the power n. Now define say capital G 0 1 power n to sorry. That's fine. To by G of say f equal to summation n equal to 1 to infinity fn by 10 to the power n. So then you can find that if f not equal to g, so that imply or you can say that if f not equal to g and fg both belongs to 0 1 power n, that is fg are the function from natural number to 0 1. So they are not same. So that imply there exists n such that fn is not equal to f of g, right? So that imply you can say that in the
Fn is not equal to g of n.
oh sorry, thank you. G of n, that's been in decimal representation of g of f and g of g, the nth what should I say, nth entries. Entries are different. Okay, so this is an injective function. So that imply g of f is not equal to g of g. So that imply g is injective. Okay, so these are the clever trick. So there are many problems this kind of you can search or you can generate and you can do that one. So for an example, this one I did by myself. Maybe this is available in any book. So there are many proofs. There are many ways to prove that this has the same cardinality. So actually I prove it in my way and I like this one. So it is easy to find a surjective function. It is easy to find a injective function. So we are done. But if you look for if you search in internet, if you find this one, then maybe you will find a different proof. Okay, so it is not the only way to prove this one. There are many ways to prove this. So this has the same cardinality. So till now we proved that power set of n, it has the same cardinality of this one, and that is the same cardinality of 0, 1. Now how can you prove that cardinality of 0, 1 equal to cardinality of R?
Sir, I think before we prove that like cardinality of 0, 1 closed is equal to cardinality of 0, 1 open.
Ha.
And then cot pi
It,
x will go from 0, 1 to
right,
all real numbers.
right. So we have already proved that um, this equal to open 0, 1. We defined a bijective function, right? We did not define. No, we defined.
Like I think we did for like just one, just like 1 included, 0
Ha
excluded.
ha 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 ha.
But like same logic can be applied.
Right, right, right. But right, in other ways also you can find, first of all, you can find the injective function. Say this is R. You can define a bijective function f from this to this by defining just f of x equal to say x minus half by x into x minus 1. Okay, so this is bijective. Because half point it is 0 and near 0 it goes to infinity, minus infinity, near 1. Yeah, near 1. No, near 0. Just a minute. Where it is goes to infinity or to minus infinity? Near 0.
Minus infinity.
Right.
So it is going to plus infinity. I guess.
Huh.
Yeah, it goes to like plus, right? Like if you take 0 plus,
Yeah,
then
and right, right. But it is going to somewhere minus infinity plus infinity. Okay. Right. So
We
it
can
is
have it like
bijective.
1 by 2 minus x.
Ha.
Okay,
So
okay, okay.
if you take near 1, then that will be positive, that will be negative, that will be positive. So it is positive, negative infinity. And if you take near 0, then that will be negative, that will be negative. So it is ultimately positive. So plus infinity. Right. So you get it is a bijective function. So that's mean cardinality of R is same as cardinality of 0, 1. Right. And in other words also, so 0, 1 subset of closed 0, 1. So that imply cardinality of closed 0, 1 less than equal to R. So we have this equivalent. Again, this is this. Yes, 0, 1 subset of R. So we are done. So that imply cardinality of R is same as cardinality of 0, 1 is cardinality of 0, 1. Okay, so you can play with all of this, right? And we have also proved that this is same as cardinality of 0, 1 n, cardinality of power set of n. So we have proved that again this is equal to cardinality of R minus Q. So all have the same cardinality. And everything is same as the notation by that LF naught, LF1. Okay. Now, right, since I don't
Sir,
have time.
can you,
Huh,
sir, excuse me. Sir,
huh.
can you tell me how did we get the bijective function that x minus, how is it bijective?
So this one,
Yes, sir.
just prove it is just a set theoretic argument actually. You just prove that this is bijective. You can find one y and then you can find one pre-image, and if you take two function and then you can prove it is bijective. You just do by yourself. That is easy.
Okay, sir.
because it is intuitively it is clear. So at half it is going to 0, and at 1 it goes to some infinity. It goes to, if you look at the curve, it is going to that plus infinity to minus infinity. Or better to write, it is half minus x, then you will get a minus infinity to infinity. Okay. Then actually the curve will be like this. I think this way. Something like that. Okay, now these are the homework. You like more problems, right? So this is same as this. Okay, and another one. What is the cardinality of the collection of all cardinality of the collection? Okay, collection of all continuous function from R to R. Okay, so these two is your homework. Try to solve this. Okay, so there are many problems actually. If you want to search in internet, you will find this kind of many problems, and you should try those. Okay, so this is up to our syllabus. So I hope that there will be no problem when you face the problems in your minor examination. So do you have any quick comments? The time is almost over, so you can ask if you have any comments or something. Oh, there is a question. Oh, Magrawal. What is? G is an arbitrary function belong to this. Oh, it is your answer? It is your
Yeah,
answer?
it was just a clarification, I think.
Okay, okay, okay. Thank you, thank you. Yes, so we can stop and see you in the next lecture with the first lecture of combinatorics, and all the best for your minor. I always confused minor 1 and minor 2 because previously we had two minors, minor 1 and minor 2. And because of this COVID situation, our semester was little bit squeezed. So we now have only one minor. And remember one thing, since it is recording, so you should not copy from others because some of you are from MTL 100 batch, and you have seen that there are few students who got caught uh, after the cheating and they got 0 marks. So same rule will apply here as well. Okay, there is a little bit chance also, maybe near 0% chance, so maybe 1 or 2% chance that you will cheat, but you will not get caught. There is a chance of that one as well, but there is a good chance that if you cheat, then you will get caught, and in that case you will get 0. So there will be no compromise, there will be no minor or exam for that one. You will get 0 for every question. So I hope you will solve problem by yourself only. Okay, all the best. See you in the next lecture. Okay.